So, good morning again. We should start this session. Before introducing the first speaker, I have some recommendations from the technical staff for all speakers of this session. Please be here above the light. So, Dieudonné, please, the first one. When talking, please do not give back. because of us, but also because of those that are at home. Okay, we don't remember this, but at the end it is fine to be aware of this. And speak close to the microphone and above the light. Okay, Dieudonné? And so it is my pleasure now to introduce the first speaker of this session. Is Professor Mbounna. Dieudonné Mbounna, no professor, from the University of Seville in Spain. So Dieudonné, you have here, the talk is about the characterization of some classical and semiclassical orthogonal polynomials on lattices. So the floor is yours, please.
Thanks for giving me the floor, and I would like to thank the organizer for giving me this opportunity to speak. And it is a pleasure for me to be here because I was the second and the last PhD student of Professor José Carlos Petronilo. And that's why during this talk I decided to present some last results that we were working on. And unfortunately, he could not get see this work published before passing away, and yeah, that is very sad. So, before starting the presentation, I would like to share with you our first contact. It was at the end of 2016 when I arrived at the University of Coimbra, and because of the visas problem, and arrived almost at the end of the first semester. And directly after that, I discovered that there was a course on orthogonal polynomials in the program, and that course was supposed to be held in the second semester. And I sent him an email saying that I would like to, if possible, to do my PhD studies on that. And immediately, he responded positively to my email, and during the first contact, his first question to me was, do you know the mathematician Jean Dieudonné? I said no, but he said that, oh, because maybe you can be, maybe you are one of his family members, but it was a joke. Yeah, so during this talk, what we are going to do, sorry. So what we are going to do is to start with the definition of an orthogonal polynomial sequence. So we suppose that we have a simple set of polynomial called Pn. We said that it is an orthogonal polynomial sequence with respect to an element in the dual base if there exists a non-zero complex sequence that we are going to call here Hn, such that whenever we apply U to the product Pn Pk, we always have Hn times the Kronecker symbol delta at n and k. We also say that the functional U is regular. So it is well known that orthogonal polynomial sequences satisfy a three-term recurrence relations where we have two coefficients in the relations, as you can see, Bn's and Cn's, with Bn's complex sequences and Cn's are non-zero complex sequences. If you are in the case of positive, definitive, or orthogonal polynomial sequence, it is required that Bn's are real and Cn's are positive. And in that case, we say that it is positive, definite with respect, it is defined, it is regular with respect to a positive measure. So what we call lattice here is this mapping where we have two expressions. The first expression with Q different from 1 is the Q quadratic lattice when we assume that C1, C2 is different from 0. And the second one when the Q equals to 1 is called the quadratic lattice, when C4 is different from 0. And we define also two sequences, alpha n and gamma n, that you are going to see a lot during this presentation. And after that, we are going to define two operators called dx and xx in the space of polynomial, and by transposition, we will define the corresponding operator in the dual space. So that is what we are going to do here. Dx, xx, and in the dual space, that's how we define them. So, what we call classical orthogonal polynomials here, like we are in the space, we are considering that we are talking about the theory of orthogonal polynomials on lattices. So we say that a regular functional is classical if it satisfies these Pearson type equations, where the polynomial phi and psi are of degree 2 and 1, at most 2 and 1 respectively. So here we are going to give some characterization of this type of polynomials. So the first one that we call C1 is the definition that we just saw, like if you have a regular functional, then if there exists two polynomial phi and psi, so that the Pearson equation holds with degrees and most 2 and 1 respectively, we have a classical. And the second one is that the sequence of derivative with respect to the operator dx is also an orthogonal polynomial sequence. This is the hand characterization. And the third one is that each element of the sequence Sx of pi n can be always written as a linear combination of 3 consecutive terms of the derivative sequence, being the last coefficient be different from 0. The fourth one is that we can always find two polynomials, phi and psi, such that this second order difference equation holds. And this is the Dieudonné type characterization. And there are many other characterizations, and we would like to mention that these characterizations are due to several authors, but there is one paper where the authors try to prove all these equivalence at once, but we found that there are some mistakes in the paper. And so what we did, our contribution was in this situ where we proved something more than this. It was the synonym hand problem. Like if this problem was posed by Ismael in his monogram of 2005, and the problem was the following. If you have an orthogonal polynomial sequence Pn, if for some fixed k, the sequence dk of pi n is also an orthogonal polynomial sequence, then we have a classical orthogonal polynomial sequence, and that is what we proved. This one was a result proof with Kenya, and this characterization C3 was proved by Marcelin and Roberto Costa, and this one C4 was proved by Murad Ismail. Yes. Now, this is our fundamental question. We suppose that we have a non-zero functional satisfying the Pearson equations where we wrote the expression for polynomial phi and psi. We would like to know what are the necessary and sufficient conditions only based on these parameters A, B, C, D, and E, such that we guarantee the existence of an orthogonal polynomial sequence. And we were able to answer this question. That is, we need a sequence Dn and the other sequence phi n of C3 minus En over D2n, both different from 0. And here we define those sequences in terms of A, B, C, D, E, and also the sequence alpha n and gamma n that we define. After this, so when we suppose that this condition holds, we now know that all sequences of derivatives with respect to the operator dx are also orthogonal polynomial sequences. And so in this slide, what we did is to give the coefficients of the 3-term recurrence relation of all those sequences of derivatives with respect to the operator dx. Now, the proof is the following picture. And this picture was taken in 2000, near the end of 2019 by Renato during his visit at the University of Coimbra, and that is the period where we were working on this, and you can see on the blackboard some kind of introduction to this, and we share many things together, and that's how when we were working on this. So what are the related families? And it was shown that up to an affine transformation of the variable, the related orthogonal polynomial sequences are the Askew-Wilson polynomials, including specific and limiting cases. And here we provide the coefficient Bn and Cn for the three-term recurrence relation of that polynomials, but we would like to add that there are several cases of this polynomial in the literature. And why? That is because orthogonal polynomials, and in fact the classical one, appear in very different form in the literature. And that is why during this work we try to unify all this in a single theory. That's what we did. So you have, for example, the Q-Racard, the continuous dual hand, and so on. And so what we are going to do now is to move to a second conjecture that we solved, and this conjecture was also made by Ismail in his monogram of 2005, where he said that if you have a polynomial of degree at most 2, that we prefer to write here as az squared plus bz plus c, such that this structural relation holds, then the related orthogonal polynomial sequence Pn satisfying this are the continuous Jacobi polynomials or the Alsalam-Char polynomials, including specific and limiting cases. And we were very interested to solve this problem because this equation is well known in the theory of orthogonal polynomial, I mean the theory of classical ones, because if you replace the dx operator by the standard derivative, I mean d over dx, then you have a full characterization of what we call a classical orthogonal polynomial with respect to a continuous variable. I mean the Hermite, the Laguerre, the Bessel, and the Jacobi polynomials. If you replace the operator dx here by the Q-Jackson operator, dq, or even the Han operator, dq omega, up to an affine transformation of the variable, you will see that it is also a characterization of what we call Q, the classical Q polynomials. There are in total 12 plus 2 others that was found by Renato and co-authors. So for this, it was very strange for us that when we have this operator on lattices, we don't have the full characterization of Askew-Wilson polynomial, but just some specific cases. And when we were starting this, we thought that maybe this conjecture is not true, but even in substance, we will see that there is something wrong with this conjecture. So what we did is first to prove that if we have an orthogonal polynomial sequences satisfying that equation, then it is a classical orthogonal polynomials. So we show that there are two polynomials, phi and psi, of degree, I mean here it is psi, of degree exactly 1 for psi, and for phi it is a polynomial of degree and most 2, such that the Pearson equation holds. But at this point, the proof is not over because you can see that the polynomials phi and psi are in terms of some other parameters that are involved in the equations. That is why what we are going to do next is to show that the coefficients Bn and Cn of the polynomials Pn satisfying that equation fulfill a system of difference equations. And here we will see that are involved the parameter Cn, the coefficient that we have in the structural relation, and also the coefficients of the polynomials. That's why, in general, to solve this system, it is not easy, but some of them can be solved very easily. Like, for example, the first equation can be solved, the second one, and even the third one. But after that, this one is not so easy to solve. And even there is a fourth one where everything is mixed. So We will solve our problem taking into account three facts. First, initial conditions. This is because we know that classical orthogonal polynomials can be entirely determined by only the three first terms of the polynomials. And so, if we have initial condition where we have like B0, B1, C1, and C2, that information is enough to identify the polynomial because we already know that they are classical. So we know how the coefficients look like in general. What we are going to do is combine all this information, knowing that they are solution of this system, to give a positive answer to this problem. So we will answer positively this part, but I will later on come back to the second part of this conjecture. So now the situation of semi-classical orthogonal polynomials is the situation where we have a regular functional U satisfying the same Pearson type equations, but here we allowed the degree of the polynomial phi to be anything but no zero. And we allow also the degree of the polynomial psi not to be 1 necessarily, but greater than 1, greater or equals to 1. And now the second characterization is the hand characterization, which is instead of the derivative sequence to be also an OPS here, it is quasi-orthogonal. That is the difference, and the definition here is given. And the third characterization is that this second order structural relation holds where in this site you can see a combination, a linear combination of terms, PNs, contrary to the classical one. And regarding semi-classical families, these families are difficult to describe. And that's why most of the time in the literature, they appear in a very strange way depending on the problem that we are solving. For example, in this problem, we will see that the semi-classical orthogonal polynomials are involved. What we were doing here is to consider the same structural relation that was posed in that other conjecture of Ismail, but the only change is that instead of multiplying a polynomial of degree, a fixed polynomial of degree 2 times the dx of pi n, in this side of the inequality of the equality, we put a polynomial of degree 1 and the operator sx. And this still makes sense because the operator sx conserves the degree of the polynomial, but the dx is a lowering operator, meaning that it reduces by 1 the degree of any polynomial. And so we ask again the same question: what are the orthogonal polynomial solutions? What we were able to prove here is that the polynomial involved solution of this equation fulfill the same system of difference equation that we had in the other case. But in this case, we saw that the polynomial solutions are not classical but semi-classical. And that's why sometimes these operators in the literature are called companion operator because they share some kind of similar properties. And here, since we don't know that, we don't know how to find the semi-classical families, we were able to describe some of them. For example, we proved that this classical, in fact, it is a specific case of a classical family, the continuous dual hand. We found that this polynomial is a solution of the system. More precisely, we proved that this equation holds. And later on, what we did is to manipulate that equation to arrive to this other equation that we have here in blue. And actually, this equation appears to be a counterexample to the second part of the conjecture, because Ismail said that the solutions of that equation remain unchanged if we allow the polynomial, the fixed polynomial pi to be a of any degree, and if we add more term in the right-hand side of the equality. And so, clearly here we have a counterexample. And even more, in a very recent work with Kenya, we showed that This structural relation is related to the semi-classical orthogonal polynomials theory, and we were even able to find a new family belonging to the semi-classical one, and it is symmetric of class 2, and that family appears also to be a counterexample to other conjecture that was claimed to be proved in the literature by some other authors. And here I would like to share with you these last pictures that were taken during my thesis defense, and I still remember what we were talking about during these pictures. And in fact, after the thesis defense, when Kenya was taking this picture, Professor Petronino told me, but Mbounna, you got the maximum classification. Why are you not smiling? I said, but Prof, I have the mask. How can I smile under the mask? Who will see? Who will notice? He told me, okay, then you can remove your mask. And that's how we took this picture, because it was during the COVID period. Thank you very much.
Thank you, Dieudonné, for your presentation and also for sharing with us these moments with Petronillo. Thank you very much. Are there any questions or comments to Dieudonné, even about something connected with PhD or other questions? Dieudonné, I have a question. I'm not absolutely from your area,
yes.
But when you said at a certain point that you have tried to unify the theory for many classes of the polynomials,
yes.
For me it was not clear that you were able to arrive to this objective. Were you able to unify that theory for all classical polynomials?
I mean, the classical, what I present here is for the classical orthogonal polynomial on lattices.
Mm-hmm.
Yes, but even before that, the first one, as Renatos presented during the first day of this meeting, this work was, he started with the standard derivative, and he was able to unify that, and later on, when I arrived, we extend that to the hand operator.
Okay.
Yes, and this now is the other work where we did it for the
Lattice.
classical OPS on lattices.
Okay,
Yes.
thank you. Thank you.
Welcome.
So you have been clear, no one has questions to you. Let's thank Dieudonné again.